So we are going to do the 2018 Putnam problem A5. Let some function f from the real numbers to the real numbers be an infinitely differentiable function satisfying f of 0 equals 0, f of 1 equals 1, and f of x is greater than or equal to 0 for all x in the real numbers. Show that there exists a positive integer n and a real number x such that the nth derivative of f at x is less than 0. This is another situation where proof by contradiction or by contrapositive is going to be useful. And the reason for that is f of 0 equals 0, f of 1 equals 1, and f of x is greater than or equal to 0 don't really give us that much information. If we're just looking at some function on the real numbers, there's not a lot we can derive from these three conditions alone. On the other hand, let's look at what happens when we use contradiction or contrapositive. In that case, we're going to assume that this final statement is false. In other words, for all integers n and all real numbers x, we want the nth derivative of f at x to be greater than or equal to 0. This is a very restrictive condition. It gives us a ton of information because it's talking about every single derivative at every single real number. So we can do a lot of different calculations with this, which means it's going to be helpful to start from here instead. Now, when we do this type of proof, we're going to start with the assumption that the conclusion is false. And we want to show that the conclusion being false implies that something in the premises must be false. So one of these original conditions has to be false. In order to show that, we only have to pick one and show that that one is false. So let's think about which one of these is going to be the easiest to prove false if we assume the rest of them are true. We definitely need an infinitely differentiable function, and f of 0 equals 0 is probably going to be helpful as well, since we're looking at functions being greater than or equal to 0. We also want f of x being greater than or equal to 0 because that's this condition except we're plugging in the integer n equals 0. That just gives us an extra number at the beginning. So now our goal is to prove that f of 1 is not equal to 1 if we assume everything else that we just said. To do that, we need to investigate the set of functions that satisfy this identity. So let's take a look at what functions we're considering. We want f of 0 to equal 0, and we want this identity to hold true for all n elements of the positive integers or 0. These two conditions define a set of functions, and we are going to name this set so that we can do some more work with it. We're going to call S the set of functions from the real numbers to the real numbers such that these two identities will hold for that function. And now we're going to take a look at the properties of those functions. Now for simplicity, instead of calling this set S, we're going to call the set U, and we are going to call the functions in this set ultraconvex, with convex usually talking about, for example, a positive second derivative. We want to look at the properties of ultraconvex functions. And because we know we're looking at infinitely differentiable functions that satisfy an identity related to the derivatives of all orders, maybe it would help to start by thinking about how this set relates to derivatives. Let's say we have some function f that is ultraconvex. In that case, is the derivative of f also an ultraconvex function? Well, if we're looking at the idea of derivatives, it might also help to take a look at some graphs. What would a graph of an ultraconvex function look like? Well, first of all, remember that f of 0 is equal to 0. If we want to show that f prime is ultraconvex, we also need to show that f prime of 0 is equal to 0, which means that around the origin, we have a flat slope. What does this function look like in the negative values of x? Well, we know that f of 0 equals 0, and we also know if we put n equals 1 into this inequality that f prime of x is always greater than or equal to 0. this function always has either a positive or a zero derivative. Now, if we had any values for x less than 0, where the function were positive, the only way to get from here to f of 0 equals 0 is by going down, which means because we're looking at an infinitely differentiable and therefore continuous function, we need to have a negative slope to get down there. But we know we cannot have a negative slope because f prime of x is always greater than or equal to 0, which means for x less than 0, we can never have a point up here where the output of the function is greater than 0. On the other hand, we know that the values can't be less than 0 because f of x is greater than or equal to 0 for all real numbers. That's what happens when we plug n equals 0 into this identity here. So for x less than 0, the function can't be positive and it can't be negative, which means for all values of x less than 0, this function's output has to be exactly 0. And the only way for this function to be infinitely differentiable and have values of the function equal to 0 all the way up to 0 is if the slope at 0 is also equal to 0. So if we took the derivative from the left, we had to get 0 here because the slope is flat up to 0. If this is infinitely differentiable, the derivative from the left is equal to the derivative from the right, which is the actual derivative. And therefore, we've proved that because f of x equals 0 for all x less than 0, f prime must also be ultraconvex. That's because we just showed the first condition, which is that f prime of 0 equals 0. The other condition is that derivatives of all orders are non-negative. For the original function f, that means that f prime and f double prime and f triple prime and so on are non-negative. But f prime, the derivative, has those exact same functions as its derivatives. So if f is ultraconvex and f prime shares those same derivatives, then f prime will also have all non-negative derivatives, so it will be ultraconvex. This is a super important identity, and it's going to let us derive a lot of extra information. So now that we have this important identity about ultraconvex functions, we're going to take a look at some properties of these functions and see if we can use the idea of derivatives to get extra information. First of all, we know that because the derivative of this function is always greater than or equal to 0, the function is increasing, it's monotone. In other words, if some value x is less than or equal to a higher value h, then f of x is less than or equal to f of h, for f being ultraconvex. Here's the thing, if f is ultraconvex, f prime is also ultraconvex. This identity holds for all ultraconvex functions, which means it also holds for the derivatives of those original functions. F prime of x is less than or equal to f prime of h. From here, we can try to use an integral to get back to the original function f. So let's say that x is greater than or equal to 0. In that case, on the range from 0 to h, this inequality will be true for any value we plug in to f prime. So if we take the integral from 0 to some value x of f prime of t dt, the inside value of this integral, f prime of t, on 0 to x, for x less than or equal to h, that must be less than or equal to f prime of h. So the integral of f prime of t must also be less than or equal to the integral of f prime of h. Over here, we're just integrating a derivative with respect to t, so we're going to get f of x minus f of 0, which is just 0. That's less than or equal to, over here we're integrating a constant, so we're going to get the length of this interval, which is x, times f prime of h. This inequality here is an identity that holds for all ultraconvex functions where x is greater than or equal to 0 and less than or equal to h. That means that this identity also holds for the derivative of f, which is an ultraconvex function. So f prime of x is less than or equal to x times f prime prime, which is the double prime, of h. From here, we're going to do exactly the same thing that we did in the first step. We're going to do the integral from 0 to x and plug in t for these values of x here. So for any value of t between 0 and h, we know that f prime of t must be less than or equal to t times f double prime of h. So if this integrand is always less than or equal to this integrand on this interval, then we can take their integrals and the inequality will still be true. On the left, we again just have an ordinary integral of a derivative, so we will get f of x minus f of 0 is 0. Less than or equal to, over here now we have the integral from 0 to x of t dt. So we're going to get t squared over 2 times f double prime of h. And you can probably guess what the next step is. We know that if this is true for f of x, it's also true for f prime of x. And we can keep doing this integration that we've done so far. Let's look at the pattern of what's happening with this inequality and generalize it to an arbitrary value of n. If we do that, we're going to have f of x is less than or equal to what we have on the right side for an arbitrary value of n. Now with every step that we apply, we're going from f to f prime, which means that the derivative of h is going to keep going up by 1 as we apply each step. So let's think about how this expression is going to progress as we integrate over and over again. We have t squared over 2 times f double prime of h. If we integrate this with respect to t, what we're going to get is t to the third over 2 times 3, which is 3 factorial. And then since we go from f to f prime to do that, we'll have f triple prime of h. If we do it again, we're going to have t to the fourth over 4 factorial, since 4 times 3 factorial gives us 4 factorial. And then with an extra step, we're going to go from the third to the fourth derivative. In general, we will have t to the n over n factorial times the nth derivative of f evaluated at h. Remember that the value of h was arbitrary. We just picked it to be some value greater than or equal to 0. So this is actually true in all cases where 0 is less than x is less than h. And we can pick any value of h that we want. So this is the first piece of information that we're going to need to solve this problem. I'll also point out that I made a little mistake in notation here. I was talking about t to the n over n factorial, but actually because we evaluated that integral at the bound of x, it would be x to the n over n factorial right here. Now there's not much more information we can get from this identity by itself. We've already proved it for an arbitrary integer n, but from here we need to take a step back and look at some other piece of information that we can use to combine and get an actual proof. From here, we need to go back to the original question and think about what other identities we might derive. In this case, we're looking at an infinitely differentiable function. Is there any other identity that relates to an infinite number of derivatives? Well, there is one that calculus students know very well, and that is the Taylor series expansion. And another thing that might make you think it would be a good idea to use the Taylor series expansion is that right here, x to the n over n factorial times the nth derivative of f, that is the nth term in a Taylor polynomial. So this looks a lot like a Taylor series. Maybe we should use the idea of a Taylor series on our ultraconvex function f. In order to do that, I'm going to use an identity that I derived in a previous video. You can check the link in the description for that, about the error bound on a Taylor series. I'm going to use one specific form of the error bound on a Taylor series in this video, but if you know another form of, for example, the Taylor inequality, the reasoning is analogous for other forms. I'm going to use one specific form here. The error between a function f of x and its nth order Taylor polynomial is equal to the integral from a to x, where a is the center of that Taylor series, of the n plus 1th derivative evaluated at t times x minus t to the n over n factorial dt. Again, check the description for this derivation. So this is the exact error for a Taylor polynomial. Now let's think about if we can find anything unique about this error term for an ultraconvex function. Remember that an ultraconvex function has all derivatives greater than or equal to 0. We see a derivative right here. So we know that this part of the integrand is strictly non-negative. It's greater than or equal to 0. What about the rest of this integrand? We know that n factorial is greater than 0, and on the interval from a to x minus t is going to be positive because t is less than x. That means that this part is greater than or equal to 0, and this part is greater than or equal to 0 as well. That means that we know if a is less than x, then this integral is greater than or equal to 0. So for a less than x, we have this inequality right here, and by the transitive property of inequality, we have that f of x minus the nth order Taylor polynomial is greater than or equal to 0. If we add t sub n of x on both sides, we're going to get that f of x is greater than or equal to the nth order Taylor polynomial, which we can write as the sum from k equals 0 to n of the kth derivative of f evaluated at a over k factorial times x minus a to the power of k. So from that integral, we know that if a is less than x, then this inequality is true. And notice that the inside of this sum has the exact same form as that integrand that we just looked at, which means that each of the parts of this sum are also greater than or equal to 0 for x greater than a, and therefore this sum is greater than or equal to 0. What this means is that for every value of n, this sum is bounded by f of x and 0. All of the terms in this series are positive, and for a monotone bounded series, we know that the sum must converge. This sum converges to a finite value. And there is one important property that we can derive from that. Remember that the test for divergence talks about the limit as k approaches infinity of the inside of a sum. And the test for divergence says that if this limit is not 0, then the sum diverges. In this case, we know the sum converges. It does not diverge. And therefore, this limit must be equal to 0. This limit is very suspiciously similar to the term that we have right here. So what we want to do now is take the two pieces of information that we have here and put them together to get the information we need for our proof. Now, in order to combine these two pieces of information, we need to make these inside terms look as similar as possible. There are a few differences right now that we want to try to eliminate so that we can put them together. For example, on the left side we have x minus a to the power of k. But over here, we just have x to the power of n. We really want to have the inside of this power of k to just be x by itself, like it is over here. In order to do that, you might think to plug in a equals 0. But that's not actually the step we want to take here. And the reason is, we're really looking for information about the value of f of 1. Remember, at the very beginning of this problem-solving process, we assumed all of the original conditions were true except f of 1 equals 1. And our whole goal is to prove that f of 1 is not equal to 1 under the conditions we have here. If we plug in a equals 0, we're going to be looking at the kth derivative of f, but evaluated as 0. And the thing is, we already know what the kth derivative of f at 0 is. F of 0 equals 0. And if f is ultraconvex, f prime is also ultraconvex, which means f prime of 0 is 0, f double prime of 0 is 0, any derivative of f evaluated as 0 is 0. We don't need any information for a equals 0, so that's not going to help us here. We really want information about a equals 1. Now, if we plug in a equals 1, on the inside here, like we said before, we're going to get x minus 1 to the power of k, which is definitely not what we have over here. We want to try to make those two look similar. But there's something else we can do in order to accomplish that. Because x in this expression is a dummy variable. All we need is that x is greater than a. So we could let some other variable be a substitution that we put in place of x to turn this inside into just one variable to the power of k. Right now on the inside, we're going to get x minus 1. So let's let u equal x minus 1. If we do this substitution, we're going to get on the inside of these parentheses u by itself to the power of k, exactly what we want. So let's see what happens when we do these two substitutions into this limit. We're going to get if 1 for a is less than x, in this case if we add 1 on both sides, is going to be u plus 1. Or in other words, if we subtract 1 here, we're going to get if u is greater than 0. Then the limit as k approaches infinity of f kth derivative of 1 over k factorial times u to the k equals 0. So now we want to make this expression on the right match what we have over here. And we can do that if we plug in h equals 1. Remember, our only restriction on h was that it was greater than or equal to 0. So let's say h is equal to 1. And we can substitute n equals k because n and k are both dummy variables in this case. That means over here, we're going to get f of x is less than or equal to x to the k over k factorial times the kth derivative of f evaluated at 1. And look at that. This expression is exactly the same as what we have over here, with the difference of x versus u. But that doesn't matter because, like we said before, u is a dummy variable. We could easily put if x is greater than 0, then x in here. So we're almost there. We have two expressions that look almost identical, and we need to make sure that we're careful of the bounds as we do the next few steps. This identity over here is true for x greater than 0. And this identity is true for x between 0 and 1. So, with those two together, the bounds for both of these identities being true are x greater than 0 and less than or equal to 1. So on that interval, we have f of x is less than or equal to x to the k over k factorial times the kth derivative of f at 1. And the other piece of information we have is with an ultraconvex function, we know that this f of x must be greater than or equal to 0. What we're going to do now is take the limit of every part of this inequality. We can use the squeeze theorem. So we're going to use the squeeze theorem to take the limit as k approaches infinity of each part of this inequality. And by the squeeze theorem, this inequality will still hold after we take the limit. The important thing to note here is that we're taking the limit as k approaches infinity, which means that x is not affected by this limit process at all. We just have x greater than 0 and less than or equal to 1. Now if we do this limit, the limit of 0 is just going to be 0. And the limit of f of x is just going to be f of x. That's not with respect to k at all. But over here, we have the limit as k approaches infinity of x to the k over k factorial times the kth derivative of f evaluated at 1. That limit right here is equal to 0 on that interval. So we have f of x being greater than or equal to 0 and less than or equal to 0, meaning f of x is exactly equal to 0 on the interval from 0 to 1, including the value of 1. And our goal was to prove f of 1 is not equal to 1. Well, in fact, f of 1 is definitely not equal to 1 because f of 1 is equal to 0. And that completes the proof. So I actually really like this problem, and the reason that I like it is that it uses a lot of the most basic and fundamental aspects of problem solving. The idea of experimenting with the fundamental properties of a setup, such as the idea of being infinitely differentiable and of the derivatives being positive, thinking about how that relates to the ideas of the derivatives of ultraconvex functions, and then taking two identities that look so similar and trying to put them together. The important thing to take away from this process of problem solving is that to solve a problem where you don't know how to initially approach it, you want to experiment with the most fundamental properties of the setup. Now, when I make a video like this, I'm only presenting the steps that lead to the solution. If you were doing this in actually a math competition or independently trying to solve a problem, you might not immediately pick up on the one step that's going to get us to the solution. But playing around with those things is how you make the important breakthroughs in getting to the solution. Thinking about the idea of ultraconvex functions, talking about derivatives, led us to the idea of what if we look at the function's derivative? Is the derivative of an ultraconvex function ultraconvex? That was our first breakthrough. Then we thought about the idea of, well, we're looking at an infinitely differentiable function. What does this function's Taylor series look like? That would be an infinite number of derivatives. And then by looking at that inequality, we got the other piece of information that we needed. All of that just came from playing around with the setup and thinking about what ideas were sort of related to the things we were really trying to solve. Once we did that enough playing around, we got two different expressions, and then by making them match up, we could put them together and get to our final solution.